Okay, so let's take a look at some Chapter 4 review problems. I'm going to first take a look at page 252, question number 7. This is a communication problem. And it says a cup of hot liquid was left to cool in a room temperature that was 20 degrees Celsius. The temperature changes with time according to this function. This is the function that they give you, 80 half to the power of t over 30 plus 20. Use your knowledge of transformations to sketch this function. Explain the meaning of the y-intercept and the asymptote in the context of this problem. Now, if you take a look at this, if there was no 20 here, this is actually a very, very easy problem because what this is actually talking about is half-life. See, the base is a half, okay? And the initial temperature, if there was no 20 here, the initial temperature would be 80. And also, the fact that the exponent is t over 30 means that every 30 minutes, let's say, the temperature of this liquid is cutting in half. So right at the beginning it would be 80. And then 30 minutes later it would be half of that, which is 40. And then 30 minutes later it would be half of that, which is 20. And then 30 minutes later it would be half of that, which is 10. And then 5, and then 2.5, and so forth. But if you take a look at this, this has a plus 20 at the very end, which is not a big deal because you could still do the half-life of all that stuff every 30 minutes, but then every answer you have to add 20 to it. So it's still the half-life of 80 every 30 minutes, but at the end of every single calculation you do, you have to add 20 to it. So let's come up with a table of values and let's actually graph this thing. This is time and temperature as a function of time. So we already know things are happening in 30s, okay? This half-life stuff is happening in 30s. So if I plug in a 0 initial temperature, you have to understand that you could actually go out and plug in a 0 into this formula if you wish, okay? But there's a much easier way of doing this. So if you plug in a 0 into this formula, this is going to be temperature at time 0 is equal to 80. A half to the power of, that's 0 divided by 30, which is 0, plus 20. So this is temperature at time 0 is going to be equal to 80 times a half to the power of 0 is just 1. Anything to the power of 0 is 1. So temperature is going to be equal to, there's that 80, but then you're adding 20 to it. So again, if there was no 20 here, this would be very easy. The initial temperature is 80, okay? But it's not. You have to add 20 to this. So that's what I'm going to do. I'm going to add 20 to this. So this is temperature at time 0 is equal to 100. Okay, so temperature at time 0 is equal to 100. So the temperature is not 80 at the beginning. It's 80, but then there's this 20 hanging out always with the problem. So again, if there was nothing here, the initial temperature would be 80, and then after half an hour, that 80 would be cut in half, it would be 40. And then after another 30 minutes, the 40 would be cut in half, it would be 20. But just remember, there's always this plus 20 happening at the end. So the initial is not just 80, it's 80 and then plus 20, which is 100. Now, we know that stuff is happening after every 30 minutes. So it'd be 30, 60, 90, 120 even, if we wanted 5 points. Now, I'm going to use what I know about this. And what I know about these functions is that in reality, this initial temperature is the 80, but then plus 20. Now, what happens after 30 minutes? Remember, what happens after 30 minutes is that 80 is cut in half. So if I cut 80 in half, it's going to be 40, but then I have this plus 20 hanging out. So that's going to be 60, okay? So if I plugged in a 30 into this, you can actually plug it in and you would get an answer of 60. Okay? And then, again, after another half hour, that 40 is being cut in half again. So that 40 is going to be cut in half, so it's now 20. But then this plus 20 is hanging out, so you're going to get a total of 40. And then after that, another 30 minutes, that 20 is going to be cut in half, which is 10. But then you have this plus 20 hanging out at the end, so it's going to give you 30. And then after another 30 minutes, that 10 is going to be cut in half, so it's going to be 5. And then you're going to add 20 to it, so it's going to be 25. And then after another 30, if you wish, this 5 is going to be cut in half, which is 2.5, but that 20 is going to be hanging out, so it's going to be 22.5. So if you don't understand that, based on what we've been doing, if you do not understand that, you could just plug in 30 into the formula, you're going to get 60. You could plug in 60, you're going to get 40. You plug in 90. The biggest point here is that you're going up by increments of 30 because something is happening every 30 minutes. Okay. Now, of course, you can go and graph this. So you go to graph this thing here. You're going to end up with time and temperature as a function of time. And if you come up with a nice table of values, this is going to go up by increments of 30. So 30, 60, 90, 120, 150, 180. So these are going up by 30s. And then this can go up by, well, you know that you have to get up to 100. So maybe you want to go up by 20s or 10s. Okay, so 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, so I've gone up by increments of 10. So my first point is 0, 100, which is right about here. My second point is going to be 30, 60, which is right about there. My third point is 60, 40, right there. My next point is 90, 30, which is right there. My next point is 120, 25, which is right there. My next point is 150, 22.5. And then it's going to look like this. And it's going to go on forever, like that. Now, what affects the equation of the horizontal asymptote? From last section, what affects it is if there's a C value. See, if you take a look at the problem again, it says the room temperature is 20 degrees Celsius. So obviously the hot cup of liquid coming into the room is going to get colder and colder until it gets closer and closer to room temperature, and room temperature is 20 degrees Celsius. See, the equation of the horizontal asymptote here is y equals 20, or sorry, temperature is equal to 20. And what does that mean in regards to the problem? The cup of hot liquid is going to get closer and closer to room temperature, which is 20. Now, what is the y-intercept? The y-intercept is clearly 100. It's when x is equal to 0. The y-intercept is 100 degrees, okay? 100 degrees Celsius. And that means that the cup of hot liquid starts at 100 degrees Celsius. Okay? So let's move along. We're going to look at page 262. So let's just flip to 262. And if I look at page 262, question number 6. Question number 6 says, a species of bacteria has a population of 500 at noon. It doubles every 10 hours. The function that models the growth of the population P at any hour T is equal to this. It says, why is the exponent T over 10? Well, the exponent is T over 10 for question A because this doubles every 10 minutes. So something is happening every 10 minutes. That is why it's over 10. It's not happening every hour. It's happening every 10 minutes. Okay? Then, question B. Why is the base 2? So why is the base 2? The base is 2 because it is also the common ratio, doubling. You are doubling. That's the common ratio. Question C. Why is the multiplier 500? The multiplier is 500 because the initial amount is 500. Question D. Determine the population at midnight. So if I wanted to determine the population at midnight, remember the population is 500 at noon. So at 12 o'clock, it's 500. It doubles every 10 hours. Okay, so it doubles every 10 hours. What's the population at midnight? Well, midnight is 12 hours later, so I'm going to plug in population 12 hours later. I'm not plugging in 12 because that's the time. That's the time after the initial. It's 12 hours later, so this is 500 times 2 to the power of 12 over 10. Okay, so this is going to be P at 12 is equal to 500 times 2 to the power of, this is just 1.2. And so if I do that on a calculator, remember, you can just use your calculator to do this. So this is population at time 12 is equal to, just make sure that when you do this problem, that you are actually doing 2 to the power of 1.2 first. So I'm going to go 2 to the power of 1.2 equals, and then I'm going to multiply that by 500. And that will give me 1,148. And you have to round to the nearest whole. Now it's actually 1,148.6, but you can't round up because it hasn't become a full bacteria yet. So you only have that much bacteria and one headed on the way. Don't round up, round to the nearest, round down, because this is not a money question. This is how many bacteria there are. Okay? And so it says, it also has another one that says determine the time at which the population exceeds 2,000. I'll actually let you do that one on your own. It deals with logs, but I'm going to move on to the next one. And actually, when I get to a log question, I will do that one for you. So let's see this one, question 9. It says, a student records the internal temperature of a hot sandwich that has been left to cool on a kitchen counter. It also says that the room temperature is 19 degrees. An equation that models the situation is this here. And this should make sense from the last question that we were doing, because 19 degrees is room temperature. So the sandwich is going to start off, now again, this is half-life, and every 10 minutes the sandwich is getting colder, okay? And it's going to get colder and colder until it reaches 19 degrees, which is the room temperature. Okay. Now, what was the temperature of the sandwich when she began recording its temperature? So it wants the initial temperature. Initial temperature happens at time equals 0. So if I plug in time equals 0, I'm going to get 0 over 10 plus 19. So the temperature at time 0 is going to be equal to 63 times 0.5 to the power of 0 plus 19. So this is going to be temperature at time 0 is going to be equal to 63 times, that's going to be 1 plus 19, so 63 plus 19. Exactly what we should have remembered, because that's the initial usually if there's nothing here. But remember, now the initial is going to be 63 plus 19. So that's what we get, 63 plus 19, which is 82 degrees Celsius. Okay? So the temperature of this hot sandwich is 82 degrees Celsius right at the beginning. B, determine the temperature to the nearest degree of the sandwich after 20 minutes. Well, that's easy. Just plug in a 20 for T. I'm going to let you do that one on your own. But C, this is the one. It says, how much time did it take for the sandwich to reach an eternal temperature of 30 degrees? So if you want to know when the temperature, is going to be equal to 30 degrees Celsius. When? What time? So I already know that the equation is 63 times 0.5 to the power of T over 10 plus 19. So what I'm plugging in is the temperature is equal to 30. So I'm going to plug that in over here. And I'm going to have to solve for this. Now, how do I solve for this? Well, I'm going to solve one thing at a time. I'm going to try to isolate for T, bring the 19 over. This is going to be 63 times 0.5 to the power of T over 10 is equal to 30 minus 19. So 63 times 0.5 to the power of T over 10 is going to be equal to, this minus this is 11. And so if I continue this, I will have to divide both sides by the 63 out in front. Okay, and that will get rid of this for me. And so I'm going to have 0.5 to the power of T over 10 is equal to, and I would take this on my calculator,